So shall we get started? So where did we leave in the last class? So it was on Tuesday. So how many were in the Tuesday's class? Okay, so we started on lined canals and we are designing lined channels. And first what we looked at is how the Manning's roughness would change for an unlined canal, and then what would be the difference for Manning's N for the two unlined and lined canals. Let's say this is the Manning's N for an unlined canal where you have sediment. Now what would be the Manning's N for a lined canal? So it would reduce because we are smoothing the surface, so it would reduce up to maybe 0.014 or 0.015. And using this Manning's N, we have designed a canal for discharging the same amount of water but at a reduced flow depth. We are reducing the resistance so that we are increasing the velocity, and so the flow depth drops down. And now we are going to see a trapezoidal section where the edges are, instead of being sharp edges, we are rounding them as a circle or an arc in the edges. And now we want to design a section like this. So we did one similar example on last class. So this is a triangular section, and instead of having a sharp edge, we considered the bottom to be curved, and then we calculated what is the area for this triangular section, what would be the perimeter. Now we have to do the same thing for a trapezoidal section. So first we need to calculate what would be the cross-sectional area for it. So here, instead of having a sharp edge like this, we are having a curved section, and we are also increasing the wetted perimeter. So if we have a curved surface, we are increasing the wetted perimeter. So here maybe if the velocities are high, at these points maybe we will start to see the sediment eroding at the sharp edges. So to avoid that, we are increasing the wetted perimeter so the velocities on the borders is slightly reduced, and so we can protect the corners from erosion. So now we have to calculate what would be the area for this section where we have an arc. So how do we start with the areas? So we have the angles theta. So the side slopes have an angle theta, and then let's say this is at right angles. So this is a trapezoid but with a curved edge. So our bottom width would reduce from this edge to this edge. Now it's only focused in the center region, because from here the channel starts to curve up, so it is not bottom width anymore. So what would be the total area for this section? So we have multiple parts. So one, we have a rectangle in the middle, and then we have a sector, and we have a triangle. And similarly on the other side, we have a sector and a triangle. So we need to combine all those to get the total area. Y square, theta is inside, plus cot theta. So by is for the rectangle. So what is the area of this triangle? So area, do you get a different area or the same? Same. And what about the perimeter?
plus 2y theta plus cos theta.
2y theta plus 1. So do you get this for the perimeter? What about the perimeter, wetted perimeter? So this is what you should get for the area and the perimeter. Now, once we got the relationship for A and P, let's try to do an example how you can use this. So let's say I want to discharge 350 meter cube per second, and the side slopes for 1.5 horizontal to 1 vertical. The longitudinal slope is 1 in 5000. And the Manning's end is 0.015. So this is the data that we have, and based on this we need to calculate what would be the bottom width B and what is Y. So how do we get? So we have two unknowns. So we need to find the two equations which we can solve to get the two unknowns. So how do we use the discharge? Let's say 2 meters per second is the maximum permissible velocity in that channel. So we cannot exceed 2 meters per second. And if we exceed 2 meters per second, then we can see eroding of the concrete or whichever lining we are using. So for that reason, let's say we are limiting it to 2 meters per second. So what is the first parameter we can calculate based on Q and V? Area. How much is the area? 175. And so we got the area. So do we have one set of equation? So we have one equation. So this is 175 now. So we have an equation. And now we need to find the other equation. So what is this equal to? And how do we find the vector perimeter? Yes. So we have these three values which we can use in the Manning's. So if you use the Manning's equation, you would get what is the hydraulic radius R. So what do you get for R? Hydraulic radius? 3. and the wetted perimeter P. Eight point eight. 58.8. So do you get the same answers roughly?
formula उनका
So what about the values? Done. So now you have to solve these two equations to get B and Y. So what do you get for B and Y? So what is the width?
$52.368.
52.3, 42 point. And what about the depth?
Corresponding to this depth is 3.47.
3.47. So do you all get the same or close values? Alright, so shall we move on? Okay. Alright. So I think you are familiar with these terms. Gradually varying flow, rapidly varying flow, and uniform flow. Right? So now we have 4 rows. So one of you please step in from each row and identify where is gradually varied flow and rapidly varied flow and uniform flow in this. So as a team you can pick somebody. So just identify one zone as rapidly or gradually varied flow. So who wants to come from here? Come on, we don't have time. I mean, it doesn't have to be right. So don't be shy. Who wants to come from here? Yeah, just mark it. It's a, yeah, only one. Just mark the section where it begins and where it ends. Good. Thanks. And from here, who wants to come from here? Starting and ending. So where does it start and where does it end? What about here? So I'm coming back there. You want it? Yes. Okay. So you can pick among those 3. Among those 3, whichever you observe. And from here, last one. Come on, we don't have time. Don't be shy. So who wants to come? Nobody? I think you know it. Let's start. Okay, anyway, so do we observe uniform flow in this? So the uniform flow depends on the length. So if you have sufficiently long channel so that the flow depth stabilizes, then you would observe uniform flow. So the rapidly varied flow, you marked it. So this is rapidly varied flow, and this is also rapidly varied flow. And if this distance is long, then you might observe gradually varied flow between those two. And again, same here. So this is rapidly varied flow. And if you have long distance, you might see gradually varied flow here. Now, I wanted to bring this in context of canals. So imagine this is our canal, and along the canal, we are now placing some structures. And what we are going to start looking at is how do we calculate these profiles. And first thing is we need to identify the type of profile we expect, and then how do we calculate the profile. So that is what we are going to get started on. Now, you are also familiar with subcritical flow and supercritical flow. So where do you observe subcritical and supercritical in this channel? So let's say, so what is this in between? What is this laddu? Hydraulic jump. So now, where do we observe supercritical flow and subcritical flow, either before or after the jump? Before? So I'm writing both critical, but we still need to decide whether this is subcritical or supercritical. So subcritical, supercritical. Yes, so this is supercritical, and this is subcritical. And why do we observe this hydraulic jump in between? So because the high velocity is merging with low velocity, so to lose that energy, hydraulic jump forms. Now, let's say we are looking from the top. This is our canal, and there is flow here in this direction. And I have put a bridge on the canal. So if I put a bridge on the canal, of course the flow is going to get disturbed. Let's say if the incoming flow is subcritical, do you see the flow disturbances propagating upstream or downstream or both? So because of these structures, now the flow has disturbed. So it is going to create some waves on the surface. So which direction do they propagate into? So if it is subcritical, then you would see the disturbances propagating both ways, so predominantly backwards to the upstream direction. And in case of supercritical, yes, so in supercritical it is only going to be in the downstream direction. Now based on this, what are our control points? So if I want to calculate what this profile is, and this is our subcritical profile, so what is my control point? And what is a control point? Firstly,
Where we can observe what is the
yes, so control point is where we have the information, flow information, and based on this control point, we are going to calculate what the profile is going to look like, how long the profile is going to change. Now for a subcritical flow, where is that control going to be? Either, let's say this is our subcritical flow, is the control point going to be on the downstream end or the upstream end? So if it is a subcritical flow, this is our control point, and if we have information at this point, then we can calculate what this profile is going to look like. And what about this section where we have supercritical flow? So for supercritical flow, it is going to be on the upstream. So for subcritical, it is on the downstream, and we are calculating the properties on the upstream. For supercritical flow, the control point is on the upstream, and we calculate the properties downstream. Now let's say this is our channel bed, and we have a water surface that is sloping down. So this is our GBF, where this is our flow profile, and then we have the total energy line. So this is the energy line. So let's say I want to define some terms. The bed slope, I want to denote it by S naught, and the slope of the water surface would be dy by dx, and the slope of the energy line let's say SF. Now what we are trying to get at is, let's say we have a slope, and we know that there is a mild slope, and we are going to see how to classify the slopes, whether it is mild or steep. And if we want to construct a weir, what kind of profile do we expect on it? So this is what we are going to arrive at. So to do that, what we are going to do is consider the total energy. So what is E for open channel flow? Yeah, so this is the specific energy. So which is Y plus V square over 2G plus Z. And if I take the gradient of it with respect to X, this is what you get. Now since the bed is sweeping down, I want to represent by a negative sign. So let's look at this term, V square over 2G. Now what would this become? So let's say we want to consider Q and A, so in terms of discharge and area. Now what would this be if you differentiate it? differentiating with respect to y, which is the flow depth. And this is what you would get. Now dA by dy is area divided by the depth, and I want to represent that with a top width d. So this term I am replacing with the depth, with the width.
Sir, so what we do here, first we differentiate it with respect to x. So in upper section, dv square upon dx into 2.
Q square
So first in other line.
above.
Yes, sir. So
Uh-huh.
d
Yes.
square divided by dx into 2 remains at d. Differentiating with respect to x.
Yes.
And so the below line, what we do?
So here we brought in y. So we are doing differentiation with respect to y, and so we have dy by dx.
Sir, after that again we are differentiating with respect to y.
Now instead of doing with x, we are just doing with y, and we brought in this term. So you have a dy here and dy.
So instead of doing differentiation with dx, if we doing with dy, then how we getting the term dx in the derivative?
So here we have another term, right? So dy by dx. So we are replacing dx.
यार नहीं देखा यार ये नहीं पढ़ा
So whatever is being differentiated with respect to x, now we are doing with respect to y. And then we have another term dy by dx. So instead of differentiating with respect to x, we are doing with y, and we have this term dy by dx. So we are still preserving this dx, so we are not eliminating it. Now what we did was to convert this v square or 2g into a function of dy by dx. So because we have dy by dx here, so we are eliminating that v square over 2g. So now if I use these two terms, if I bring in the SF and S naught, so minus S naught is for dz by dx. So this is what you would get. Now we are interested in how the flow depth is varying with x, the distance x. So if we find this relationship, then we are going to use the control point and calculate backwards what the flow profile is going to be. So this is the relation that you would get for dy by dx. Now, So this term would be your fruit number. If you rearrange the fruit number, v square over 2g. This is what your fruit number is going to be. Now, if you remember the critical depth calculation, so that is q square over g to the power 1 by 3. So this would be a function of the critical depth. And then we have the area and the top width. So this would be the area is proportional to the flow depth. So this is a function of the critical depth, and this is the flow depth. So what you would get is S0 minus SL. Some function of yc by y. And based on this equation, we will see how we can classify the flow profiles, right? So that would be in tomorrow's class. All right. So thank you.